Hi, my name is Enzo Stacy, and today I'll be talking about basic combinatorial game theory and its application to chess. For the sake of brevity and navigation, I'll be dividing this up into a playlist of hopefully 8 or 9 videos. Now let's start, like all things do, at the beginning, with a quick and nasty introduction to combinatorial game theory. Combinatorial game is played between two players who both have perfect information of the game. This excludes games like poker, battleship, and anything where information is just outright unavailable to one player. The game is made of positions and moves where any player has a collection of moves to different positions of the game, and moves alternate between left and right, shirts and skins, black and white, what have you. A position is defined as a set of left options and right options, where all the options for left are all the moves that are available to left, and all the options for right are the moves that are available for right. Position and game kind of have the same definition. They've been used interchangeably. The game ends when a position is reached where a player may no longer make a legal move. The normal play convention is that this is the player that loses. The misère player convention is that this is the player that wins. Generally, we only consider games which must end and may not be drawn. Games of such a nature may be represented by a tree where each vertex is a position connected to other positions by possible moves. This establishes a tree because games that necessarily terminate and can't be drawn must have a finite number of positions and cannot repeat, giving no cycles. Chess poses a problem for both of these conditions, which we may deal with later. As a matter of fact, games themselves may be played on these trees if you either color edges by whose move it is, or strictly rule that moves may only go left for left moves and right for right moves. To demonstrate, let's show 4 simple games. Starting with our leftmost game, we have the zero game. This is the simplest and most trivial game. The collection of moves on either side is empty, neither left nor right has a move, so the first to move simply loses. In our second game, left has one move available, and that returns to the zero position. Right has absolutely no moves available, so regardless of whose turn it is to move first, left wins. In our third game, right is the only one who has a legal move, returning back to the zero position. Left has absolutely no move available to him. Right wins regardless of whose turn it is. These games are given the values 1 and -1 respectively. Our fourth game is not a number. It's called the star position. Either player has one move available to them, and it's to move the game to the zero position. Once the game is returned back to the zero position, the next player compelled to move is the one that loses. This game is a win for the first player, regardless of whether they're left or right. These games are 0, positive, negative, and fuzzy respectively. 0 meaning the first player loses, positive meaning left wins, negative meaning right wins. Fuzzy means that the first player always wins. Addition is defined by playing multiple games simultaneously, making a turn on whatever tree you'd like. Addition of integer-valued games form a group and operate how you'd expect addition and counting to operate. The star position, and all positions derived from it, like up and down, have odd properties, the sum of 2 stars being 0. Further trees are constructed by taking simple games as options themselves, and defined by what games when added together make a 0 game. 2 halves in the -1 game make a 0 game, and up is a negative down, 3 ones make 3, and so on. Games immediately derived from the star position, like up and down respectively, are often fuzzy and less than any real-valued game, so they're called infinitesimal. They offer an advantage, but not as much as a real-valued game, even a fraction, like 1/2 or 1/4.